Okay, good morning, ladies and gentlemen. We will be finishing up 2.1 double A day 2 today. Sandwich theorem, this is not on your note sheet. You can write it down here in a minute. I'm going to skip over this first for a particular reason. I'm going to skip over this. We're going to look at a special limit here. Okay, now this special limit, past years, this little squirrel has been on the AP test in some fashion or other, whether it's free response, if it's uh, multiple choice. I have seen this guy on there almost every year. There's a faster way to do it than memorizing this limit. Right now, we need to memorize this limit. We need to know this special limit, that the limit as the limit as x approaches specifically 0 of sine x over x approaches 1. Okay? Now, what we're going to do is we're going to evaluate this little bugger quick, okay? And we're going to look at this and we're going to say, hey, what the heck is the sine of 0 divided by 0? The sine of 0 is what? The sine of 0 is 0 over 0. Whoa, what is that? That's a hole. There's a hole in the function. Remember what that means. That means find the limit because it exists. Find the limit. It's there. Now, this is not an easy one to do. Algebraically, this is kind of a beast. There's not really a lot we can do with this because what have we been doing? We've been factoring. Well, there's really nothing to factor. The whole fraction that's sitting there, sine x over x, the whole thing's pretty basic. There's really nothing I can do at the top or the bottom. I do have a whole bunch of trig identities I could use, but sine x is pretty basic, and when we use those, we usually try to write things in terms of sine and cosine usually, and I'm already there, okay? Well, back in the day, this is not a fun special limit to show. I remember when I saw it the first time in my life, I was like, what? I don't know what the heck you're talking about there. What are you talking about? So what we're going to do is good thing here in our life now, we have what is called graphing technology. I want to view this something. We have our graphing calculators. Good thing we got the graphing calculators because we will use this limit to prove the rest of this stuff. And this is actually a very easy limit to see with graphing technology. Please make sure, I'm going to menu, I'm going to check my settings because I'm graphing trig. I have to be in radians. I am okay. Then I'm going to come back and I'm going to say control divide. And I want to see, what am I? I am sine x over x. And what I'm going to do is look at that interesting little graph. And before I go further, I'm just going to stretch this graph out. I'd like to see a little bit more of it. So what I'm going to do is I'm going to change my windows and my Windows settings. And I'm going to go from, because we're talking trig, I'm going to go from, remember, pi and 2 pi. I'm going to go from negative 20 to 20. And I don't need to see quite as tall the way that looks. So I'm going to go from like maybe negative 3 to 3. And what I see is as x approaches infinity, this is pretty interesting. As x approaches infinity, what is y approaching? There is not a horizontal asymptote. This little rascal is oscillating back and forth, yet the infinite limit is approaching 0. How in the heck can that be approaching 0? That is really super strange. I need to make sure that I turn something off here. And okay, I got it, I think. So as I'm going out to infinity, what I see is I see this thing is oscillating closer and closer and closer to 0. It's pretty interesting. Why does that happen? Well, think about it. When I'm looking at the top here, I want red. When I'm looking at the top here, my sine function is always going to be oscillating between negative 1 and 1, depending where it is on the unit circle. And the bottom is x, so this numerator is always outputting that. This is always outputting, as I go to infinity, it's outputting bigger and bigger and bigger, okay? So, bigger and bigger and bigger. So what is it when I take a finite number anywhere between -1 to 1 and I divide it by a number that's bigger and bigger and bigger? Well, that number gets smaller and smaller and smaller. Hence, that's why we can see this wiggle and squiggle is getting lower and lower and lower. It's pretty interesting. I like this graph. It's kind of interesting. And when I think of it, we're like, oh, sine. It's a sine function in there. What is the period of sine? The period of sine is 2 pi. Wonder what the distance is from here to here after I hit that. From there to there. Wonder how much is in there. I'll bet you it's 2 pi. I'm not going to take the time to look, but I'll bet you it's 2 pi. So basically what we're doing is we're looking here, and we're looking for the limit as x approaches 0. Okay? And as x approaches 0, sure, now I can't see my scale. And I want to make that 1. Sure looks like it's approaching 1 for the limit, doesn't it? And I can use my calculator. Good thing I got my calculator because we have graphing technology. I can direct substitute that in there, and I can say menu. I can trace my graph, and I can type in a 0. Ooh, it's undefined. But we're smarter than that because we know with the calculator, as long as we get close to 0, oh, I plugged in 0.1. Well, that's 0.998. 0.01. Well, that's 0.999983. 0.001. Oh, and I can even trick my calculator into telling me it's 1 on this particular problem, okay? And that's coming in from the right. Well, how about from the left? How about -0.1? Well, I'm getting close to, I can see down there in the bottom. How about -0.01? Yeah, definitely it's 1. I can see I'm approaching 1 from that side, okay? There is an algebraic way to prove this limit, and it was not fun for a while, but it's super easy when we are looking at the graph. Now, how are we going to use this? And hopefully you can wrap your mind around my trig, why I'm saying this is always oscillating between -1 and 1. And think about your unit circle. As you went through your quadrant answers, we went around the circle. There's pi, there's 2 pi, and these numbers repeated. And when I'm thinking of what was my maximum here for the sine, wasn't it? Was that 0, 1. Plot your point, 0, 1. That was the high point, and the low point was between 0, -1. And everywhere in between here was bigger or smaller than -1, so that's where I see that oscillation coming. And when I divide it by a number that's getting bigger and bigger, whoop, Mr. G, my wavelength height is getting smaller and smaller and smaller, and it does not have a horizontal asymptote, really important to understand, but it does have a limit, and the limit would be approaching 0 as an infinite limit. Okay, and as it approaches infinity at 0, as it approaches -infinity at 0, as I approach 0, this limit is 1. Well, I just screwed that up. That's okay. So what I'm going to do is I'm going to use this limit. Okay? I'm going to use this understanding. How am I supposed to remember that, Mr. Kruger? Well, it's one of those things. You need to know it. Okay. There is a fast way around this later on. It's something called L'Hopital's rule. Well, why are you teaching us this? Why are you telling us we need to memorize it? Well, first, we're going to have to use the concept up there first so we can algebraically apply that property to algebraically find limits. And we're also going to use this to define what the squeeze theorem is. And I can't give you L'Hopital's rule yet because you don't know how to find a derivative yet. And if you don't know how to find a derivative yet, you can't use L'Hopital's rule. So there, that's why. But I'm going to come back here now, and we're going to talk about the sandwich theorem. And it's exactly as it says, okay? Now my f of x function right here, that f of x function, that f of x, I'm going to let be sine x over x. Because somehow some books will use the sandwich theorem to prove this. Not some, they all do, in some way, shape, or form. And what the sandwich theorem basically says, okay, is if I can find a function around that limit, the limit we're talking about right now, around that limit at 0, around that limit value, that is above it, okay? And above it is going to be my h of x function. And I can find another function around that same limit value, but that's always below it. That's going to be my g of x function, okay? And these two, g and h, okay, and their limits as they approach that c value, in this case, to prove this, and my c value is 0, if the limit of g of x is the same as the limit of f of x, and that limit is L, because f of x is sandwiched between these two functions, then the limit of f of x as x approaches c has to be L. What? Well, I'll show you. It's easy to see with a graph. Some books don't call it the sandwich theorem. Some books call it the squeeze theorem. Okay? Whether you're squeezing something or you're sandwiching something, it's the same thing. So the beautiful thing is you are not going to have to come up with your g of x function and your h of x function. I'm going to tell you what we're going to use, okay? What we are going to look at, we are going to say our lower function, g of x, we're going to say g of x is always equal to cosine x. And we are going to also say h of x, my upper function, is going to be x squared plus 1. And what we're going to see is when this is my f of x function in the middle, this function is always below the f of x function. This one is always above the f of x function for all x within a realistic window around 0. What the crap are you talking about? Well, let me come right back to my cool little calculator here. And inside here, I already have sine x over x. This window's a little bit bigger than I want it to be. So what I'm going to do is I'm going to change my windows here quick. And as I'm coming through, I'm going to be putting, what do I put? I want my x's to go from -5 because I want to keep it close to around 0. And I'm going to make that 1. And then my y's, yeah, what do I want my y's to be? I think I want -5. Whoa. Yeah, no, that's okay. Crumb to 5. And hopefully I can see enough there. And actually, I don't like the way that is, so I'm going to change this to a -10. And I'm going to keep that one at 10. I'm just going to leave my y value. Okay, so now I'm going to add in my graph. So I'm going to add in my upper graph of x squared plus 1. And as I'm around 0, as I'm around my target value here, obviously, hopefully it's obvious, that x squared plus 1 is always above my f of x function. The other function I'm going to choose to graph in here, I'm going to choose to graph my cosine function because I like trig. So there's my cosine function, and as I am in this area around 0, okay, within reason, within, well, where are we talking? 1, 2, 3, 4, and 1, 2, 3, 4. So between 4 and -4. So if I would have left this at, if I went to -4, and I change this to 4, within this window of opportunity, the red graph is always on top of the blue one, and the black one is always underneath it within reason here, okay? Now, when I look at this, if I trace my graph, I think I can trace my graph with all 3 functions. Trace graph, I want to trace it at 0. Notice, down here, I'm not at 0. I'm going to type in a 0, and I'm going to enter it. 0, undefined. That's my blue graph. That's my sine x over x. That's my 0 over 0. Now, as you're tracing, I think if I up arrow, see how it turns red? The red one goes through 0, 1. And if I use my down arrow, I can go down to the black one. My black one is also 0, 1. So this is what the squeeze or sandwich theorem says, is because the black graph is always below the blue one, the red one's always above the blue one. In the limit of the red and black, as x approaches 0, the limits of those are 1. Because the limits are those, and I can see as I zoom in, and I can continually zoom in right here as I wish. As I zoom in on there, come on, give me my zoom in. I can look in and I can see how the red and the black graph sandwich the blue graph in there for all the x's between -4 and 4. Red's always bigger, black's always smaller, yet they're red and black equal at 0. And their limits are 1, therefore the limit of the sine x over x also has to equal 1. That is what the sandwich theorem says. How are we going to use this? Well, it's something you need to know. Sorry. When we hit L'Hopital's rule, it's not for a long time yet, we will be able to apply L'Hopital's rule to this function, and we'll be able to see that limit is 1. Pretty easy. Easier than we normally would. However, we're not there, okay? You don't know derivatives. So what we're going to do is we're going to use that special limit. And even before I do that, there's another numerical way to think about this, okay? And as I look at the sine graph, I want to pull my calculator back up here, and I want to add a page, and I just want to look at I got to erase all that crap. I want to add a page. I want to graph. I want to graph just the plain old sine x, okay? Sine x, that's all I want to see here for a second. Oh, that's a pretty little color. And basically, because this limit is approaching 0, I'm looking for what's happening to my sine in here, all right? Now, when I look at this, I know this is a curve, but this, when I get really close to 0, this almost looks like the identity line. What the heck are you talking about? Well, let me take my zoom, and I'm going to zoom in right here at the origin. I'm going to zoom in, I'm going to zoom in, I'm going to zoom in. Okay? As I zoom in from -1.3 to 1.2, from below, okay, 0.82 to -0.82, this looks super linear in here. What are you saying? What I'm saying is when I plug a very small number into the sine function, it's going to output virtually that exact same number. What? Yeah, I wouldn't lie to you. So let me add a calculator page here. And what I'm saying is if I take the sine of 0.01, that is realistically going to equal virtually 0.01. Okay? If I took the sine of 0.001, that's even smaller. The closer I get to 0, the closer to exactly the same that number. What do you mean? That's like 10. No, it's not. Scientific notation. 1, 2, 3, 4. Boop. 0, 0, 0. Round it. If I rounded that to 3 decimal places, that's essentially 0.001. The closer and closer I get, the closer and closer those numbers get to each other. Sooner or later, it's going to round to the exact same thing. Well, what does that have to do with it? Well, why am I pointing that out? Well, I'm basically pointing that out because when I'm looking at this, and as I'm going to 0, the sine of x, as long as this is a really small number, the sine of x is virtually going to output x. It's going to output the same thing. So if I'm putting in 0.01, this is when I evaluate it close to 0, this is going to output, the numerator is going to output 0.01, and then because I put in 0.1 for x, it's going to be divided by 0.01, which is essentially 1. The numbers are so close, it's essentially 1, okay? And when I said, as long as I'm super close to 0, sine x is virtually going to output whatever I plugged in, and I'm plugging the same number in the top and the bottom, and that's why it's 1. Okay, we're going to use that concept here now, and I'm just going to come down, and I'm going to come down here, and I'm going to say, well, what do you think number 1 would be? Okay, sine x over x. Well, essentially, I just said, if I'm putting a number really close to 0 in there, really close to 0, I'm getting my typical things going here. If I'm putting basically super close to 0 into the sine function, it's going to output virtually the same thing. What are you talking about? We're thinking that this is going to equal 1. And it is going to equal 1 because the sine of 2x is virtually going to give me 2x as I get close to 0 over 2x. I can reduce those little rascals and I can say 1. Is it really? Well, let's check this out. What is trig sine 0.02? Right? I think that's what I was putting in, 0.02. It's basically 0.02. What's the sine of 0.03? It's virtually 0.03, okay? So as I'm putting a very small number in for my x, the whole point of this is, if I'm putting in a very small number close to 0, really small number, whatever tiny number that's there, the sign's going to basically output exactly what I put in. And it's going to end up equaling 1, okay? Can we generalize this? I think we can. I have full confidence that we can generalize this a second. What the crap are you talking about generalizing? I'm saying, what is the limit as x approaches 0 of sine ax over ax? What do you think that's going to be? Yes. Because as I'm putting a very, very small number in for x, the smaller x gets, the smaller a times x gets, the more it's going to spit out exactly what I plugged in. And I'm going to end up coming out with ax over ax. Those go away. 1, because it's the same number over the same number. Okay? So let's take a little gander here. What do you think we would get here? Now, if somebody were in class, I would expect somebody is going to come out and they're going to say 5. Because the way I just explained that is, as I'm plugging in numbers really close to 0, this sine function is realistically plugging out 5x. And it's going to get divided by x, because that's what I put in. Those x's are going to reduce, and I'm going to be left with 5, okay? That's the logic. That is not how you would have to show your work to do that, but logically, that is what happens, okay? And if you don't like that, well, let's check this out. Let's say we put in 0.01. So if I put in 0.01, I'm really taking the sine, and when I put in 0.01 times 5, that's going to be 0.05, and that's going to get divided by 0.01. Well, this is going to basically output my 0.05 divided by 0.01, which is, guess what? It's 5. But that's not how we algebraically prove it, but that is the logic through it. Here's how you need to show your work on these. Do I really have to do it that way, Mr. Kruger? Yes, you do. This is exactly what they would expect to see on the AP test. when this comes up if it were a free response. We have to apply this concept. The sine of the same thing over the same thing. We have to apply this concept. It doesn't matter if it's 2x over 2x, 3x over 3x. We have to apply the sine of x over the same thing goes to 1. Okay, that's what we need to apply. So this isn't the same thing, is it? Well, what the crap? Why can't I just go like that? Well, I can as long as I go like that on the top, because all I did was multiply that function by 1. 5 over 5 is 1. Anything times 1 is 1. And then I can look at it as the limit as x approaches 0, and I can separate this thing, and I can say, oh, okay, I really did want that sine 5x over 5x. I did really want that there, and then that's still times 5 over 1, okay? And why can I do that? Because I just wanted to make this little thing here. I can't really draw very well, but I know that limit right there, because it's the same thing over the same thing, sine is going to equal 1. So I know the limit as x approaches anything, the limit of a constant is the constant times the limit as I approach 0 of sine 5x over 5x is 1 equals 5. And that would be the work that would need to be shown on how to find it, coming up with that 5 over 5, split the fractions apart, okay? Which takes me to the next page. How about here? If I were here, I think I would have people say, well, what do you think the answer is? I believe I would have people say right away, 3/2 or 1.5. Why? Because as I go close to 0, this sine function is going to be spitting out what's right there, and it's going to get divided by what's down there. Those are gone, 2/3. But that's just a quick way to check it, okay? What we need to do is we need to split this thing up, okay? So here's what I like to do. I like to say, well, I got to get something to write with. Limit as x approaches 0. I'm a little different than this, okay? I'm always going to be breaking apart fractions. And I know I want a sine 3x, okay? I know what I want. It's going to be times by something. And I also have my 2x. Now, I know I need a 3x underneath here, okay? I do have an x. So I would keep this x right here. I wouldn't put it with the 2. And I would have slid that x right there. And then I would look at it and say, okay, well, wait. That's sine 3x over x. I need them to match, so I need it times 3. And 3 over 3 is going to give me that. So now I take the limit of the constant times the limit as I'm going to 0 of sine 3x over 3x. That's 1 equals, haha, winner, winner, chicken dinner. Okay? So we can kind of think about this the same way. I think before we can generalize this right here. I don't know if this is on your note sheet. I know my first generalization, I don't know if that was or not. I don't believe they're in the book. But this is just going to take this guy here. And if I had somebody in here and I wasn't all by my lonesome, I guarantee I'm going to have somebody that's now seeing this limit because I'm plugging in a small thing. The sine of whatever is very small, when I plug a very small number in, a times small, that's going to output exactly what I'm looking at there. And the bottom is going to be same thing. Those are going to go away. And you're right. We're going to be looking at an A over B. But we have to be able to algebraically show it using that limit. Okay? Well, it's really not that hard. So I'm going to take my limit as x approaches 0. And the way I'm looking here, I know I'm going to have a sine ax. And that needs to be over a sine ax, and I'm going to have another. I'm just taking this fraction apart, and right away, I'm seeing 1's on top, because top times top gives me sine ax. Bx times 1 gives me bx on the bottom, okay? Only thing different is I'm not putting these ones in because I don't know what I'm putting there yet. I'm going to do some factor of 1 in there. And I know this x, I don't want this x right here. I want that x to be right here. So what do I need to add? Well, I need to sine ax over ax. So if I have to multiply by an a in the denominator, I have to multiply by an a in the numerator. The limit of the constant is a over b times the limit when these guys match is 1. Winner, winner. I just nailed it. Sometimes you got to break these into 3, 4, 5 different fractions. I mean, they can get a little funky. They can get hard, okay? So we just have a couple more examples here to do. We're going to apply. So the other thing, because these were all, what was the first thing Kruger didn't do when he didn't plug this in. He should have been plugging in, seeing, oh, sine of 0 over 0, 0 over 0. I should always be substituting in first, okay? Why? Because I don't always have to go through this work. Do I have to here? Well, this is going to give me sine 0 over 0, 0 over 0 says work, okay? Well, this one looks a little bit different. So this is really limit as x approaches infinity of, okay, whenever I see, I'm not going to do a times yet, whenever I see this sine x, I need to split that into a fraction, so I'm just having a sine x over an x. And why would you put infinity there, you bonehead? It's not infinity, it's 0. They specifically told me 0, going to 0. And then what I can see here, ooh, there's a greatest common factor of an x there. So I have 2x minus 5. Oh, I can split this little rascal up. So limit x approaches 0 of times fraction, fraction. I want my sine x, and I'm going to nest that x underneath it. And I have a 2x minus 5, and there's a 1 on top. Because I can evaluate that one already, I don't need to add any constants to it. I can plug my 0 in. And when I plug 0 in, this actually equals 1 over negative 5 times, I'm not plugging 0 there. I know that limit is 1, so it's negative 1/5, okay? What else do we got on here? Tangent. Ooh, fun. It's kind of an ugly one. I love trig, if I didn't say that before. Well, what is the tangent of 0? Tangent of 0, you guessed it, it's 0. So I get 0 over 0. So I need to figure out a way, okay, I don't have a tangent x over x, I have a sine x over x as I approach 0, okay? So I got to think of my trig identities. Well, this is the limit. X approaches 0. I got an x here. Tangent, that's really sine x over cosine x. And, oh boy, I see a complex fraction. Big line. Kruger always likes to look at it as the limit as x approaches 0. I multiply by the reciprocal, which is top sine x over cosine x times the reciprocal of the bottom, which is 1 over x. I'm going to hence slip and slide these little rascals apart. Limit as x approaches 0. I want to see my sine x over my x. That's going to be times 1 over cosine x. I'm going to plug in my 0, knowing that limit's 1. 1 over cosine of 0. What is the cosine of 0? 1 over 1. This limit is 1. Okay? And how about here? Don't fall into the trap, guys. Am I approaching 0? If I'm not approaching 0, I do not want to find a form of this. I do not need to. I direct substitute in sine pi over 2 over 4 times pi over 2 What does this equal? Sine of pi over 2, 1. 4 times pi over 2, 1, 2, it's 2 pi. What's my limit? 1 over 2 pi. Do I have any more? I think I do have one more tricky one yet. I do have one more tricky one yet. Well, what am I going to do here? First, I'm going to say 0 plus sine 0 over 0. That's 0. So it's 0 over 0. Wait, this one looks like it's kind of split up, and I can't just go like that because that's a fraction. We need to see what we're going to do, and this is a key thing in calculus, okay? When I have a fraction, and I have a monomial denominator, one term, I can split that expression into multiple fractions. What are you talking about? Well, I can say this is the limit as x approaches 0 of, okay, this is really x over x plus the sine x over x, which isn't that really the same as, isn't that really x over x? Isn't that just a fancy way to say 1 plus sine x over x? The limit of a constant is a constant plus the limit as x approaches 0 of sine x over x is 1. My limit is 2. Okay? Last thing I want to show you how to do here, okay? Because lots of times in here, there's a way, there's a reason why the calculator I gave you or that you guys have been buying when we order them here, there's a reason why they're CAS, Computer Algebra System, which makes this not needed to be written twice, but because it's Computer Algebra System, it works with variables, okay? What are you talking about, Kruger? Watch this. This is Slicker and Snot. You can check any answer in your homework. You don't need the answers in the back with limits. You can pull up your calculator, and what I can do is I can go into my menu, I can go into my calculus, and I can find a limit. And I can say x, and my x is going to be approaching 0. And because when I use my side arrow, I go up there, because that little guy isn't as dark, means I don't have to use it. I can put a plus or a minus in there for right-handed and left-handed limits, which we haven't done yet. And I'm going to come right in the middle and watch what I'm going to do. I'm going to say control, divide, and I'm going to say, to check our generalization, what was the sine of a times x? What's going on here? Uh-oh. Whoa. And wonderful. I think I just don't want to do that. Okay, it came back. So I have to make sure, I don't know what I did, but I have to make sure I separate these to make sure it's not seeing multiple variables. And then if I put a B and I put a times X in there, it will give me my limit of A over B. I can type any of these limits into my calculator. For instance, when I was looking at menu, calculus, limit, x approaches 5 of, and I get in here and I do my old control divide and I type in an x squared. We already know how to do this one, but minus 25 over 3x minus 15. I don't know if you remember what that is, but if we did that, we get 0 over 0. The limit is 3.3 repeating. That would be 3 1/3 or 10/3, I believe is what we got. So you can check all your limits with the CAS. Okay? You guys have a great weekend, great night, whatever. See you next time.